It is the 4th of September, 2025, approximately 7:38 p.m. And today we're going to be continuing our observation of the exercises in thumb and foot, going back to the first chapter and exercise 8, picking up where we left off. So, camera check. Exercise 8. It says let G equal the set containing Z within the complex numbers such that Z to the n is equal to 1 for some n within the positive integers greater than 0. For 1, it asks us to prove that G is a group under multiplication. Perhaps the group of roots of unity in complex numbers, and to prove that G is not a group under addition. So what would be the intuition for this? Well, multiplicatively, every z with z to the power n equal 1 is non-zero. So inverses exist and stay in G. Products of such elements still satisfy a root of unity equation. Additively, trouble appears immediately. 1 is within the group G, but 1 plus 1, which equals 2, is not within the group G. And 0, the would-be additive identity, is not a root of unity. So, let's take a look at this more rigorously. So for the first part, we just want to prove G is a group under multiplication. And we want to have closure, identity, inverses, associativity. We want to have that. We weren't asked to prove it was abelian, so we don't have to worry about that. So let's just start with closure. Take ZW to be within G, then Z to the N is equal to 1, and W to the N is equal to 1 to the M, sorry. W to the M is equal to 1 for some NM within the positive integers. Compute ZW to the NM, and that equals Z to the NM times W to the NM, which is equal to, open parentheses, Zn to the power M, close parentheses, to the power M, open parentheses, W to the M, close parentheses, to the power N, which is equal to 1 to the power M times 1 to the power N, which in turn is equal to 1. So ZW is within G. We abstracted out to having two variables. We tested it within with the multiplicative operation. We found that it is contained within the group, ergo closure holds. So let's take a look at identity. One is within G, and this is because 1 to the power 1 is equal to 1. For any Z within the group G, well, we haven't proven it to be a group yet, but within G, 1 times Z is equal to Z times 1, which is equal to Z. Simple enough. It's the property, that's what defines an identity, and that's what one is doing here. Now, inverses. If Z is within G with Z to the N equal to 1, then Z doesn't equal 0 for one thing, and for another, Z to the negative 1, the inverse of Z exists in complex numbers. How so? Explicitly, Z to the negative 1 to the power, well, open parentheses, Z to the negative 1, close parentheses, to the power N is equal to, open parentheses, Z to the power N, close parentheses, negative 1, which is equal to 1, negative 1, which is equal to 1. So, and that's of course in there. So the inverse of Z is contained within G. So we have inverses. Now, for associativity, there's something important here to note. And that is that multiplication in the complex numbers is already associative. So we can use that inherited trait in a way to say, well, multiplication in the complex numbers is associative. Ergo, the restriction to G is associative. Thus, G satisfies closure, identity, inverses, and associativity under multiplication. Therefore, G is a group under multiplication. So, and there's more to be said about this. So, we could go on to show that it's abelian because of the fact that, well, cross product. I mean, not the cross product. The complex numbers. That whole thing. This whole thing over here. It's like the units, complex numbers. I can't remember how exactly to phrase it, but this thing here is abelian, and you could make the argument that because of the fact that that's abelian, like with associativity, it sort of carries its inheritance onto the group G, which isn't. I guess it's not like the fine step-by-step incremental approach towards proving this sort of thing. You could do that, I guess. Yeah, you could do that, but it's just, you'd have to look at cases and stuff like that, but suffice to say, it's just an inherited sort of thing. Which is enough for me personally, but I don't know. It depends on what level of rigor you want to give it. If you want to give it like absolute rigor, then you show that, but in a way it's kind of a waste of time, but it's up to you. So that's it for part A. Now let's go to part B. If you think about it, all I had to do was just erase the part that said under multiplication and just put under addition, but it's fine. So we're asked to show G is not a group under addition. So let's approach this first with closure. So 1 to the power 1 equals 1. We have 1 is within G. But 1 plus 1, well, that's equal to 2. And we run into our problem. There is no n within the integers greater than 0, the positive integers, with 2 to the n equal to 1. So that's a problem. So it's like, well, absolute value of 2n is greater than 1 for all n. And of course, still being within those positive integers. So 2 can't be in G. Ergo, G is not closed under addition. And not only is it, well, because it's not closed under addition, therefore G is not a group under addition. QED. But there's also another way to do this, right? That's as simple, or simpler, more simple. And that is to look at the failure of identity in this case. So failure of closure. Now let's look at failure of identity. Social psychological fragmentation. That's how you break. That's how you break a group. It has no closure. It has no sense of identity. Can't be reasoned with. Now, if G were an additive group, then it would contain it would contain 0 as identity. But 0 to the power of n is equal to 0, you know, n being a positive integer. Ergo, the identity, the additive identity is missing. Therefore, G is, then, you know, you continue to write not a group under addition. Very good. Let's move on to 9. So for exercise 9, we're asked to let G equal, we're not asked to let G, we're told let G equal, it's a command, let G equal the set A plus B square root of 2 within the real numbers, such that A, B are within the rationals. So, first part of this, it asks us to prove that G is a group under addition. And for the second part, it asks us to prove that non-zero elements of G form a group under multiplication. So, intuitively, how do we go about this? Well, additively, everything is linear. Sums and negatives stay in the same A plus B square root of 2 form. Multiplicatively, we rationalize the denominator, so such that A plus B square root of 2, like all of that, under 1, so open parentheses A plus B square root of 2, close parentheses, to the power of -1 is equal to A minus B square root of 2 over A squared minus 2B squared. And the denominator never vanishes unless A equals B equals 0, which would be the 0 element we exclude. So let's go about that more rigorously. Just start here, and then if we run out of space, we'll just erase and then put more on there. So let's deal with A first. This part, the first part first, of course. G is a group under addition. So, start with closure. Take arbitrary x equal to A plus B square root of 2 within the group, within set G, and y is equal to C plus D square root of 2 within the set G, with A, B, C, D within the rationals. Then x plus y is equal to A plus B square root of 2. Well, that's in parentheses, open parentheses, A plus B square root of 2, close parentheses, plus open parentheses, C plus D square root of 2, close parentheses, which is equal to A plus, open parentheses, A plus C, close parentheses, plus open parentheses, B plus D, close parentheses, square root of 2. Since A A plus C, those are with the, A plus C is within, look, so A plus C, those are within the rationals. Since A plus C is within the rationals, and B plus D is within the rationals, as is the nature of the rationals, we have X plus Y within G. Reals. So we have closure then. Under addition, we have closure. So, and I'm just going to go ahead and erase this. We don't have a lot of space to work with. So. Right. Identity. Let's go on to identity. Zero is equal to 0 plus 0 times the square root of 2. That's contained within G. And for any x is equal to a plus b square root of 2, we have x plus 0 is equal to open parentheses a plus b square root of 2, close parentheses, plus open parentheses 0 plus 0 square root of 2, close parentheses, which is equal to a plus b square root of 2, which is equal to x. So we have our identity. Now, for inverses, for x is equal to a plus b square root of 2, define negative x to equal, well, open parentheses negative a close parentheses plus open parentheses negative b close parentheses square root of 2 within G. Then x plus open parentheses negative x close parentheses, which is equal to open parentheses a minus a close parentheses plus open parentheses b minus b close parentheses square root of 2. And this is just equal to 0 plus 0 square root of 2, which is we already discussed, is in G. And, well, that equals 0. That's in G. So we have closure identity inverses. Now on to associativity. So we can kind of use this sort of inherited associativity that we had earlier. In this case with real addition, right? So, I mean, you can make the case for commutativity as well, say this thing is abelian, right? Under addition. But associativity in this case follows associativity via real addition. Right, and a simple way of really showing that, though I don't think you really have to, but let's just go ahead and do that anyways. Open parentheses x plus y, close parentheses plus c, is equal to open parentheses a plus c plus e, close parentheses plus open parentheses b plus d plus f, close parentheses square root of 2, which is equal to x plus open parentheses y plus z, close parentheses. For what? For z is equal to e plus f square root of 2. So, hence, well, actually, I don't like writing conclude or anything like that whenever I end stuff. It's just kind of, well, of course it's the conclusion. You don't need to state it's the conclusion, but you know, it's fine. We'll just put therefore G is a group under addition. Didn't ask us to prove it was abelian. You can see how, you know, real real addition also implies commutativity, but didn't ask us to do that. So G is a group under addition. That's it. That's all we needed to prove. QED. Now, let's get into part B. Right after I check that. So part B, well, the second part asks us to prove non-zero elements of G form a group under multiplication. It's funny. It's like if we tighten the noose around this thing enough, we can get it to be. You know, that's the kind of interesting subtext, I guess, that's kind of going on here. It's like, can we restrict the things of what it could be enough? so that it could be a group. Well, let's see in this case. So how would we go about defining G in this case? Well, take G with the exclusion of X, let's just say. With excluding 0, I mean to say. G excluding 0. And what you'd have is a set, a set A plus B squared contained within the original set G, such that A, B is within the rationals. However, the ordered pair AB cannot be equal to the ordered pair 0, 0. A comma B 0 cannot be equal to 0 comma 0. So yeah, so that's a good way to approach it, right? Is to like look at this. It gives you more restrictions. How would you define the new thing after the restrictions are applied to the original thing? Encode that, get that on the paper, on the board, wherever you have it, and then break down that structure, break down that object rather, and piece by piece to try and prove it's a group, and failing that, prove that it's not one. So closure in this case, there's no 0 divisors, so take x is equal to, well, we'll see about that. Take x is equal to a plus b square root of 2. This is contained within our group G. Exclusion G to the power x, is an easy way to say that. G without 0. G without 0. We'll just say G without 0. And y is equal to c plus d square root of 2 and G without 0. That's a good way of putting it, though. It's about the second. No, we'll just use this. G to the x. G to the x. We'll say G to the x, but there's a better phrase that encapsulates this. I'm missing the words, so we'll just say G to the x. Then xy is equal to, open parentheses, a plus b square root of 2, close parentheses, open parentheses, c plus d square root of 2, close parentheses, which is equal to ac plus 2bd plus, open parentheses, ad plus bc, close parentheses, square root of 2. Since AC plus 2BD contained Since AC plus 2BD is contained within the rationals, that's within the rationals, I mean to say, and AD plus BC is within the rationals, we have XY is within G. So, no. Close these together. Close that together. Now, what about the case where xy is equal to 0? What about that? So there's a part to this which follows the usual lines of, is this thing closed? Yes or no? Find that it is. But now there's this issue with the what about zero? Want to show xy is not equal to 0. i.e., that is, we want to show that AC plus QBD is equal to 0, and AD plus BC is equal to 0. Force C to equal D to equal 0. But not A or B. So let's take a look at that. If A is equal to 0, then AD plus BC is equal to 0. AD plus C is 0. AD plus BC is equal to 0. And since it's A that's equal to 0 here, we want AD plus BC equals 0. That becomes BC is equal to 0. Since we already had, like, we want to show how can this work without with our inclusion of this principle, right? That A comma B cannot equal 0 comma 0. Well, since we had that as our case, we must have B is not equal to 0. So C equals 0. Then AC plus 2BD is equal to 0 becomes (2BD is equal to 0. So D is equal to 0. Which, if you were to claim that C and D cannot equal 0, this would directly contradict that. It would directly contradict the idea that C comma D could not equal 0, would not equal 0 comma 0. Now, if running out of space, let's go ahead and use this space down here. If A didn't equal 0, from AD plus BC is equal 0, we get D is equal to negative BC over A. Substitute into AC plus 2BD equals 0. And what that gets you is AC plus 2B multiplied by open parentheses negative BC over A close parentheses is equal to 0. Let's see here. From which we can see AC squared minus 2B squared C is equal to 0. From which we can tell C. So, okay, let me explain. So, here we have that over A multiplied by A, we get A squared. We get rid of the A underneath. We have 2B squared C. So then from that we can take the C out and get C parentheses A squared minus open parentheses A squared minus 2B squared. That is equal to 0. All right. Now, what else can we say from this? Well, if so A can't equal 0, we already established that. If C equals 0, then AD plus BC is equal to AD plus 0 gives D is equal to 0. B can't equal to 0 either because A can't equal 0 in this case that we're discussing. So we're looking at, okay, so C would have to equal 0. And if C equals 0, then AD plus BC is equal to AD plus 0 gives D is equal to 0. So we can't avoid either case here. Like even if we could say A is equal to 0 and wind up with AD plus BC is equal to 0. That would become BC is equal to 0, and we'd wind up with a contradiction anyway. But if we take the assumption that A is not equal to 0, and we run it along here, along these lines, then, well, along this approach, then we'd find that C would have to equal to 0, which would imply that D is equal to 0 anyhow. So, how do I write this more formally right? Well, I'm going to have to erase some board space to get to that. we're still on closure, which I probably talked too long, so that's something. But let's go ahead and finish up closure and then get to the other things. So from all this, we can say thus a squared minus 2b squared is equal to 0. That is a over b squared is equal to 2. With a b in the rationals. And this forces a is equal to b is equal to 0. And this is because square root of 2 is not within the rationals. This forces a equal b to equal 0 because square root of 2 within that contradicting a b, therefore xy cannot, but this contradicts let me think about this. Therefore xy, therefore xy cannot equal 0. And xy is within g to the x. Closure holds. Yes, okay. AB cannot be within 0. This forces AB to be within 0 for x. So if we, but in this case, the xy which we're trying to say does not exist within the set, because we defined earlier x, y to equal square root a plus b, the open parentheses a plus b square root of 2, close parentheses, open parentheses, c plus d square root of 2. So even if a and b did equal 0, it wouldn't be the case that x, y equals 0. What? No, that doesn't add. That doesn't add up. Let me see. I may have miswritten this. Pages not equals 0. So let's see here. Let me think about this. So sometimes I gotta step back and take a look at what I wrote and see if it actually makes sense longer. So that was the initial G, and then we redefined G such that we define a different G. Takes that into account. So A plus B squared 2 is G such that AB so because of that, it's Y. Set that to the format. So each of those things can't equal 0. Neither of those things can equal 0. AC plus 2BD. So yeah, okay. Yeah, following along the train of thought that we reasoned. So it's like, well, we wanted to force each of the different variables to equal 0 to show that even if we did force these individual cases to be equal to 0, we wouldn't have that x, y is equal to 0 in any of these individual cases. But what about the case in which, so we took one of them, we set it equal to 0, right? And then we took one of them, didn't set it equal to 0. So does that show that x, y can't equal to 0? Where did we get these individual elements? Yes, okay. And the rationals, C, D, did we get those from the rationals as well? Yes. Oh, maybe that's it. Maybe we already said that it can't equal 0. Right, so balancing any part of this, either of these parts, well, actually, either of the these individual parts here. So either it must be that to get this such that could equal 0, it couldn't equal 0. So we locked it out of being equal to, we locked x, y in this case, such that it can't equal 0. We want that to be the case, that it can't equal 0. Now, the way that we define this, the way that we define these individual elements that x and y would be, depends on AB not equal to 0, 0, as well as CD to not be equal to 0, 0. Any way that we would have chosen those things to be the case, such that we wrote, within those case-by-case instances that we wrote more rigorously, we went into that and we showed that, okay, if you were to try and do that, by any means you'd violate these things, which we already used to define what x and y originally were. So because of that, x and y cannot be, the structure is logically consistent such that x and y cannot be equal to 0. Okay. That checks out. At least so far. That was a long time. But it's a good thing to have that airtight. So xy cannot equal to 0. Ergo, xy is within the set G2. The x closure holds. Now let's move on to the identity element. So for the identity element, one is equal to 1 plus 0 square root of 2, then g to the x here, and for any x equal to a plus b square root of 2, we'd have x times 1, which is equal to a plus b square root of 2 times 1 plus 0 square root of 2 is equal to a plus b square root of 2, which is equal to x. So we have our identity element there with 1. Now for inverses, let x be equal to a plus b square root of 2 be contained within g to the x. Consider x times open parentheses a minus b square root of 2, which is equal to open parentheses a plus b square root of 2, close parentheses, open parentheses 1 plus, falling back upon my notes there, this would be a plus b square root of 2, and then what would this be? Well, this would be a minus b square root of 2, which is equal to a squared minus open parentheses b square root of 2 close parentheses squared, which is equal to a squared minus 2b squared. Now, if a squared minus 2b squared is equal to 0, then I end up with the same case as earlier with a over b squared equal to 2, with a, b being in the rationals, which would imply a is equal to b, which is equal to 0. This would contradict a, b not being 0, which would contradict, like we were mentioning earlier, that was what the whole discussion was about there. X being within g to the x. So a squared minus 2b squared cannot be equal to 0. So rather, we may define the inverse of x to be equal to a minus b square root of 2 from that earlier formulation over a squared minus 2b squared, and this would be contained within g to the x. Since a over a squared minus 2b squared and negative b over a squared minus 2b squared, those are within Q. What can we say further? Let's just kind of run through here with an arrow so I can get more space. Well, we can say that x multiplied by its inverse is equal to a plus b square root of 2, close parenthesis, open parenthesis a plus b square root of 2, open parentheses a minus b square root of 2, close parentheses, all over a squared minus 2b squared, which is equal to a squared minus 2b squared over a squared minus 2b squared, which is equal to 1. Which, as we discussed earlier, that's kosher. That's contained in g to the x there. So we have inverses. Because, the identity, those things. All right. This is a longer proof than I was expecting. Well, at least in terms of like talking it out. But now we move on to associativity. So this is a case of inheriting it from, which you can't really, you can't do. I was thinking like, well, why couldn't you just do that? I was thinking like a question probably poses like, well, why couldn't you do that with the other cases? Why couldn't you just say that they are inherited? Well, it's because like those things are more, what is it, foundational to what the group we're discussing actually is than they speak anything about the reals itself. The additive property which you're using from the reals is a thing which exists outside of the group and is carried on into the thing, not so much the specific inverses and whatnot. So, well, inverse identity, closure, etc. So that's why you're able to say, things are inherited from in the case of associativity, whereas you're not able to say that about the other three cases. So associativity inherited from multiplication in the reals. So open parentheses xy, close parentheses, z is equal to x, open parentheses, y, z, close parentheses, and xy is equal to yx for all x, y, z within g to the x. So, well, so we also have commutativity here, right? So we could say it's abelian if we wanted to, but it only asks us to prove that it was a group, not to prove that it was abelian. So under multiplication, it only asks us to prove that it was a group under multiplication, not an abelian group under multiplication. So we don't even really need that part. But we verified closure in this group under multiplication, identity, inverses for every element, associativity. So we can say that g of x is a group. G to the x is a group under multiplication. So we've got time for exercise 10 here. So exercise 10, it asks us to prove that a finite group is abelian if and only if its group table is a symmetric matrix. What's the intuition of this? Well, a group table records all products G sub I, G sub J. If swapping I and J leaves the entry unchanged, then G sub I times G sub J is equal to G sub I, is equal to, so G sub I times G sub J is equal to G sub J times G sub I. For every pair, exactly the definition of abelian. So table symmetry is commutativity written as a matrix. That's the intuition there. Now, let's get to the more rigorous side of things with proof. Let's let G equal the set containing G1 all the way up to G sub 1 all the way up to G sub n be a finite group. Its group table is the n by n matrix T, which is equal to, open parentheses, T sub ij with entries, close parentheses with j, with entries, T sub ij is equal to G sub I times G sub j. And, well, what is a symmetric matrix? What determines whether or not a matrix is symmetric? Well, like, more rigorously speaking, not just, it mirrors, but a matrix is symmetric if T sub ij is equal to T sub ji for all 1 less than or equal to I j less than or equal to I comma j, sorry. 1 for all 1 less than or equal to I comma j less than or equal to n. So we said we want to prove if and only if, right? So let's go and break down those into separate cases. So let's suppose G is abelian. We want to prove if G is abelian, then the table is symmetric. Matrix-wise. Assume G sub I times G sub j is equal to G sub j times G sub I for all I j, then T sub ij is equal to G sub I times G sub j, which is equal to G sub j, G sub I. True finite group is abelian. So we're already supposing it's abelian. Yes. So this holds because it's abelian, then T sub I j is equal to G sub I times G sub j, which is equal to G sub j times G sub I. And this is for every I j. So we can then say that T is symmetric. This is by definition, I didn't write the last part here, that's very important. T sub j I. T is symmetric. Okay, that's one way. So if G is abelian, then the table is matrix, is a symmetric matrix. Now, let's go the other way. If T is a symmetric matrix, then G is abelian. Let's show that. If the table is symmetric, then G is abelian. So assume T sub ij is equal to T sub ji for all ij. Then, by definition of entries, what entries are, G sub I times G sub j is equal to T sub I sub j, T sub I sub T sub ij, which is equal to T sub ji, which is equal to G sub j times G sub I for every pair I comma j. Hence, so all elements commute. Therefore, G is abelian. We prove this both ways. So we can say a finite group is abelian if and only if its group table is symmetric. Is a symmetric matrix. Is a symmetric matrix. QED. I've got time for another one. Do I? Maybe. I think so. If I have to stop, we'll just stop. So. Exercise 11 tells us to find the orders of each element of the additive group Z mod 12 So in intuitively speaking, in addition over z mod 12, the order of x bar is the smallest k greater than 1, with k times x bar equal to kx bar. Which is equal to 0. Equivalently, we want 12 to divide kx. The obstruction is the common factor GCD of 12x. The more x shares with 12, the fewer steps it takes to hit 0 bar. So let's look at that more rigorously. Let's fix x to be an element of a set containing 0, 1. Let's do this all the way up to 11. And let D equal GCD of 12, of 12 and x. Let's write 12 is equal to D times M, and x is equal to D times x prime, with GCD of M and x prime equals 1. Then bar kx is equal to 0 bar, and only if 12 divides kx by definition of modular arithmetic, if and only if dm divides k times d, well, times, open parentheses, d x prime, close parentheses, if and only if m divides k x prime. Since GCD m x prime is equal to 1, the least k greater than or equal to 1 with m dividing k x prime is k is equal to m. Therefore, the absolute, what is it, x bar is equal to 12 over GCD 12 of 12 and x. It's the order of the element there. The order of x bar is equal to 12 over GCD over the GCD of 12 and x. So let's list these values out. So say we have ourselves a table of orders. In Z mod 12, then what we get for various values of x, say it's 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, 6 bar, 7 bar, 8 bar, 9 bar, 10 bar, 11 bar, 12 bar, is for each of these, right? So we get 1, 12, 6, 1, 12, 6, 4, 3, 12, 2, 12, 3. That'd be so. What's 8 bar? 8 bar. Yeah, that would be 3. 3, 4, 6, 12. Can't have 12 bar because that's just, Okay. So we have the explicit orders. We found the orders of each element of the additive group of the integers mod 12. Now let's check this. 3, 4 bar is equal to 12 bar, which is equal to 0. 1, 4 bar is equal to 4 bar, which is not equal to 0. 2 times 4 bar is equal to 8, which is not equal to 0. Order of 4 bar is equal to 3, which is what we got. So now let's look at another instance. 2 times 6 bar is equal to 12 bar, which is equal to 0 bar. 1 times 6 bar is equal to 6 bar, which is not equal to 0. So order of 6 bar is equal to 2. And we could do this on and on and on, right? So 4 times 3 bar is equal to 12 bar, which is equal to 0 bar, with 1, 2, 3 steps. Non-zero. Ergo, order of 3 bar is equal to 4. And this agrees with the general law that we've sort of that we've established here with the order of each of these being equal to 12 over the GCD of 12 and x, for each x listed completing the computation, completing exercise L thoroughly with both a proof and a wave, but more so just a general solution, and defined rigorously, along with different spot checks across to make sure that it's accurate. So, there we go.